Starting already. Okay, so hi everyone, I'm Matt Tetlow. I'm just going to present a little on what we did with our QB50 satellite. So I'll just share the screen. Oh. I assume you guys can see that. Yep. So basically today I want to talk about sort of the process that we went through and the lessons that we learned doing the project. So a bit of an outline. First of all, we'll talk about the design of the spacecraft and sort of why we chose the various paths that we chose. Then sort of talk a little bit about the pros and cons from a hardware and software point of view, and sort of what the lessons learned were, or some of the lessons learned for us. And then a little bit about what's next. So an intro to QB50. Now this session's probably been full of QB50, so no doubt everyone knows that it's a European Union funded project launching 50 CubeSats to study the thermosphere. So our payload was the ion and neutral mass spectrometer, which you can see on the slide here, and our job was essentially to build a spacecraft around this and fly it. So, you know, why did we do it? Well, from a scientific point of view, of course, we want to understand the thermosphere better, and I guess feed a whole lot of climate modeling and weather modeling and that kind of thing, and also support re-entry type missions or better understanding of re-entry. But the most important thing from our point of view was to develop nanosat skills and technology. So build a team of people who can do a whole lot of these tasks, and then also build some subsystems that we can then use for future missions. So we had to design, build, test, integrate, and deliver the spacecraft. And we used some COTS and some custom-built subsystems. And as I mentioned before, the value from our point of view was building the technology, building the skills, and building the team. So this slide just shows the spacecraft in various levels of development, from sort of flat sat parts in the comm system up here. There's sort of, it's all kind of partly integrated there, more integrated there, and then through the test, and then that was final delivery. This image is of the delivery in the Netherlands. So the configuration management. So the first thing you start with is the systems engineering. You have a whole lot of requirements that you have to meet, and you got to manage what functions it needs to perform in order to match these requirements, and therefore what hardware it needs to be able to do these functions. And of course, you break down into the fairly standard subsystems: power, onboard compute, attitude control, communications, and structure, of course. So we kind of looked at what was needed, what subsystems were needed, and then looked at what our skill set was. And decided we have a very strong attitude course, a guidance and control group at Adelaide Uni, and with the extended team. And we also had a very strong comms experience out at Mawson Lakes. The UniSA team developed the comms payload for FedSat and as well operate a successful ground station all the time, basically. So they have a high expertise in that area, but we didn't have any power experience at all, and we didn't have any. We hadn't really built that many PCBs. So we thought power is a critical subsystem, and it's fairly complex. So we would leave that to next time. And onboard computer as well. There are a number of onboard computers which are reasonably priced, considering the amount of development we would have to do. And we also thought they would come with a whole lot of software, which we'd be able to just sort of plug and play and just use the software as straight out the box and just sort of plug our little bits in. Also, the magnet talkers, they're embedded in the solar panels, so we instead of developing our own magnet talkers coils, and also we decided to buy the off-the-shelf ones, and also because they're fairly low, occupy a very small volume, because of course they just make the solar panel slightly thicker. Also, we needed to know where we were in order for our attitude control system to work, and we needed to know that reliably. So while we were also developing a occultation experiment which involved GPS, it wasn't going to be good enough or reliable enough, certainly as a primary navigation solution. So we bought an off-the-shelf GPS. And we developed, the in-house development was the structure, so it's fairly simple subsystem to make. Just design it as light and stiff as possible. And then the attitude control system, and then the comms system. So we have both the UHF and VHF payloads, so they're identical. So there's one UHF, one VHF, and they can be either. So it gives us, and they're also connected to their own antennas, which are got their own deployment system. So basically, it's a completely redundant comm system. Then we also had MASP, which is our occultation experiment, which is a GPS front end that just basically sucks in GPS data from a particular satellite at very high data rate and stores the data, and then we post-process that after the mission. So primary structure is just fairly, as I said, fairly simple. It's just an aluminium 6061, nothing too fancy there, just made it as light and stiff as we could. And I think we ended up with a fantastic result from a stiffness and a weight point of view. In fact, better than what you can buy off the shelf. But the problem was it was ridiculously complicated to manufacture. It had all sorts of dowels on every single face. So we got a quote to manufacture it externally, and it was over $9,000 to make it. So, you know, it wasn't a fantastic product to make like that, but certainly the experience of designing it was good fun, if nothing else. The attitude control, so functionally this is what effectively how it works. So this was entirely developed by us, both hardware and software. So the GPS, besides the GPS of course, which is the off-the-shelf GPS, that's used to give us position and time solutions. So we can't run the GPS all the time because it consumes too much power. So essentially we turn the GPS on every 12 minutes, and you basically over an orbit you kind of get a distribution of points, enough distribution of points to estimate what your current orbit is. In fact, you only need two, because the center of the Earth, if you assume it's almost a circular orbit, you only need two measurements plus the center of the Earth to define what the circle is. So you can already get a position solution after just two measurements. And then once you've got a position solution, you can project that forward each time step. So you can turn the GPS on, take a measurement, and then turn it off. And then in the background, there's an orbit projector that runs. And the orbit projector gets updated as the orbit decays slowly from the GPS updates. But it's basically the orbit projector is the primary provider of position solution. So based on your position, you know where the sun should, you know position and time, you know where the sun should be, and you know what your magnetic field vector should look like. So you can then measure those two things and then work out what the error might be. And based on that, you can estimate your attitude. So we also had gyros in there, which were just enabled us to track better when we were in eclipse. But they turned out to be not good enough, so we had to introduce an ADCS sensor as well to give us the location, basically the vector to the center of the Earth, which then made our filter, our Kalman filter, be able to use throughout the entire orbit. So once we got all the measurements, use a Kalman filter to estimate position, estimate attitude, then you use a pointing controller to work out the control solution, and then actuate the magnetorquers, the 3-axis magnetorquers, and the reaction wheel. Now the reaction wheel is interesting because it's for control of pitch and yaw, but because you spin it in a positive bias, it also acts like a bicycle wheel and prevents yaw and roll. It gives you stiffness against yaw and roll. So basically it allows you to pitch over once every orbit, but then sort of prevents you to some degree from rolling and yawing away from your desired attitude. So the hardware looks like that. This is the attitude control system. There are the sun sensors. This is a hole for the GPS antenna, which is attached to the solar panel. And that's got there's a sun sensor on each side. This, what you can see, is the nadir sensor, which is looking forward and trying to find the horizon. So basically, looking forward, you can find the circle of the horizon in front of you, and then you can use that to work out the vector to the center of the Earth. And this is the reaction wheel, or the momentum wheel, just a small brass wheel, and we can obviously control its speed fairly accurately. that's what this image here shows, what the sun looks through. Of course, when you look at it, it's just got a normal CMOS sensor in it, so we had to put a film over the lens so that it didn't obviously saturate the sensor. So we bought off the shelf, we bought our solar panels with embedded magnet talkers, so those were our 3-axis magnet talkers, and in-house we developed the algorithms both for attitude and position. We developed the entire sun sensor, including PCB manufacture. And the DIA sensor is the same, and then we built the reaction wheel. On the comms side, it was a custom-developed software-defined radio, and this was developed by the UniSA team, Bill Cowley and his group. And there's it's got a custom protocol. So the majority of teams use AX25, and we were going to use Bill was always against using that. So we decided we would use CSP, which is the CUBESAT space protocol, which is a GOM space developed protocol. And then as it turned out, we decided that didn't do what we want anyway. So we basically have a custom protocol to get our data down. Anybody can collect our data, it just gets collected as a WAV file, and then we can basically decode it. So we have a partnership with a University of Alberta in Canada, and they will collect they're our backup ground station, and they can just collect a WAV file and then send it to us. But we do have a redundant, we have basically two ground stations here in Mawson Lake, so we can use either of them, and they're completely independent. So the ground facilities, as mentioned, is just a software-defined radio and a PC, and then these 2 steerable antennas on the roof. So some observations, I guess, that we sort of came across doing this project was, we found that the PC104 stack is firstly tedious to integrate and pull apart, and it's sort of become part of the standard, and everybody makes components to that standard. So it's something that you have to certainly be compatible with, but we question whether it's the way that you would continue going forward. Also, this idea of centralized power has its limitations from a power quality point of view, and also wasted resources. There's a whole lot of switches and things that we didn't use, and some of them didn't provide the current that we wanted. So it's sort of of course it's trying to be a jack of all trades, which is great for starting off this type of endeavor. But we kind of feel it should be changed a little bit to I guess enable better integration. So one of the things that was really surprising was the COTS hardware and software not being reliable and robust. So our original thinking was do the COTS or buy COTS components for high risk components, because we figured that they would definitely work. We wouldn't have to worry about them. But we found that first of all the integration with them is very difficult, because it's a black box and you don't know what it's doing or why it's doing what it's doing. And it sort of seems that the vendors are not quite as mature in the technology as you expect. So we had a huge problem in when we were over in Canberra doing the testing, where our power system it kept on dying, and the voltage showed that it was plenty of the volts were very high, so there shouldn't have been an issue with power, but it kept dying, and we had no way of working out what it was. And so eventually we got hold of the vendor, and we're talking to them, and they basically messed up the calibration. So effectively the brain of the power system was doing something different to what the analog electronics were doing, and that really messed us around, you can imagine, and caused much angst and sort of delayed the testing, in fact. So there are a number of issues, and also I guess the quality of it. We had boards made that had mistakes in them, so they had jumper leads, diverting connections or making different connections, which for something that should be that mature, it shouldn't be the case. I mean, none of our PCBs had any errors on them; they were all just tracked. So you kind of expect that from a vendor. Also, the software wasn't the software from GomSpace. We didn't use any of it. We completely rewrote everything. Our software team thought that I guess there weren't enough checks they're not robust enough about checking what state you're in and what transition you are able to do in that state. So we basically binned all of that and did our own. But then I guess, so basically I'm here throwing stones at all the COT stuff, but then, equally developing our own hardware is also very high risk. There are all sorts of things that we found, late in the piece that we had to change, and who knows how many more things there are lurking out there that are also an issue. But this is kind of what you do in development. And this is, I guess, I think hopefully people are changing their idea to basically take on a bit of risk and try and do these things, because if you don't, then you never know. And then basically you buy them off the shelf for the rest of your life. So, we maintain it was the right thing to develop our own stuff, but, you have to bear in mind that it is a risk as well. So what are we doing next? So we've kind of done a completely new bus architecture. Now it is compatible with PC104, so you can put PC104 boards in it, but it's sort of more adaptable to 6 and 12 unit spacecraft. So basically we've got a 3, a 6 and a 12 unit modular system, and you can use obviously the components for each. Obviously you can't use a 12 unit component in a 3 unit, but you can use a 3 and a 6 in a 12 and a 3 in a 3 and a 6. So we basically changed the architecture both structurally, and it's kind of got an integrated power system in it, which is quite different to the way the power is currently done. And the other thing we've done is developed our attitude control from the sort of, I guess, low fidelity attitude control, sort of getting within sort of hopefully 2 degrees. Well, simulations show it'll get within 2 degrees, but we want to get something down to 0.1 degrees. So we've developed a 3-axis attitude control system with 3 wheels, and we've actually had one of the wheels manufactured already. It's a 3D printed titanium structure and a stainless steel wheel. And we've got all the motor controllers working for that. That was largely driven by the number of, we had a number of versions of our original reaction wheel, which didn't comply with a couple of requirements until the final version. So we had a lot of lessons learned on that. So that was a really good learning experience. Also, what you're looking at in the red image here is our prototype star tracker. So we basically we're basically going to be providing a powered pointing bus. So it's got power, attitude control, and structure. Basically you put your comms, payload, and brain in it. And I think that's all I had. So thanks.
Well, Ben is offered to type a question if there is. We will have time for one question.
If you're typing.
No questions?
Just say thank you to him.
Thanks everyone, enjoy your conference.